Welcome friends, welcome dear students in our series of lecture on novel drug delivery systems. Myself, Dr. Ajay Semilty, again with you. Today we'll be discussing the microspheres. Now we have discussed the polymers, NDDS, targeted drug delivery and pulmonary drug delivery systems. Now this is turn of microspheres, microparticulates. Now let's discuss this very important and very crucial novotrugdil system microspheres in this lecture. As far as the learning outcome is concerned, after completing this lecture, you will be able to understand the concept of microparticulate formulations, and you will be able to prepare the microspheres, and you will be able to evaluate the microspheres. We will be covering this lecture under the heads Introduction to Microparticulate Drug Delivery Systems, Types, Compositions, Methods of Preparation, and Evaluation of Microspheres. So let's define the microsphere. What is microsphere? Microsphere is a novel drug delivery system, NDDS. Microsphere is meant for delivering the drug to specific target site at a rate and concentration desired by the therapeutic regimen. However, it has also been used for the systemic circulation in the dosage forms, but the main aim when we are discussing in the NDDS is directing towards the site of action. It leads to desired therapeutic efficacy with minimum side effects and improving the overall patient compliance when we are using microspheres for delivering the drugs. Microspheres are defined as a spherical particle of size ranging from 20 to 300 micron loaded with the biologically active drug. They are free-flowing polymeric microparticles with particle size less than 300 micron. It is a structure made of a continuous phase of one or more miscible polymer in which particular drug is dispersed at either the macroscopic level in particulate level or molecular level in the say when it is dissolved in dissolution level. Often microcapsules and microspheres are used synonymously. But a microcapsule is a system that contains a well-defined core and well-defined envelope. The core can be solid, liquid or gas. The envelope is made of continuous, porous or non-porous polymeric phase. The difference between the microsphere and microcapsule is the nature of the microsphere matrix, in which there is no well-defined wall or envelope. So microsphere doesn't have any well-defined wall or envelope, while the microcapsule does have. Polymers used to prepare microspheres may be synthetic or natural both. Solid biodegradable microspheres loaded with the drug, dispersed or dissolved throughout the matrix releases the drug to the desired site of action in the controlled manner. Let's have a look in this comparative diagram. As you can see, both the microcapsule and microsphere exist in gas, solid or liquid state. Just the difference is of core. The core is there surrounded by an envelope in the microcapsules, while it is in matrix form in the microspheres. Okay, it is just like you can imagine that a spongy ball which is hollow in core and when it is wet with the water, uh, you may imagine it as a microcapsule. But again, imagine a same spongy ball which is solid. Okay, it is not hollow inside. Then you will call it as a microsphere. If you are imagining it if you are imagining it in terms of micron size. Okay. Now let's discuss what is the composition of microsphere. Drug and the polymeric carrier. They are the two major components. We have discussed a lot about the polymers, but a microparticulate carrier should be able to protect the drug. It should be able to provide the stability and release the drug in controlled manner. And it must be compatible with the drug as well as the biological environment. Okay. Moreover, the carrier should be able to target the drug to the specific site whenever desired. So let's have a quick look of on the biodegradable polymers used in drug delivery systems, specifically when you're targeting, when you are aiming for site of action, when you're targeting site of action, they may be natural. We have discussed in the polymer section also, but with specific reference to the microparticles, they may be the natural synthetic polymers may be used, or semi-synthetic polymer may be used. Among the natural polymers, animal polymers like albumin, gelatin, fibrin, casein, collagen. In animal polysaccharides, chitosan, and hyaluronic acid, and plant polysaccharide like dextrans, starch, alginic acid may be used. While in the synthetic acid, animal proteins like polylactide, glycolic acid, PLGA, animal polysaccharides, polycaprolactone, polyanhydrides, and among the plant polysaccharides, polyalkyl cyanoacrylates may be used for microsphere development. Now, let's discuss that how we will select the polymer for delivering the drug through the microparticulate. Now we want to prepare the microsphere. So if the nature of drug is hydrophilic, we will go for a hydrophobic polymer. Otherwise the drug will at once released. In the same manner, if the hydrophobic drug is there, you will use a hydrophilic polymer if you want to control the release. Okay. And this is our aim. And you can get the desired pattern of release. If the desired duration of action or desired duration of release, you can say, is up to 24 hours, then certainly you need a blend of hydrophobic as well as the hydrophilic polymer to achieve that particular control release. Because if you envelop a drug, or if you mix a hydrophilic drug with the completely hydrophobic single polymer, what will happen? That drug is not going to release at all through that matrix. It won't be able to pass across that matrix. So a blend of hydrophilic as well as hydrophobic polymer is needed, so that it is also being controlled as well as it is also being facilitated to the for diffusing out of that matrix. Okay, especially when it is going into the biological environment. Now let's discuss the method of preparation. What are the methods of preparation? There are four major preparation methods you can classify. However, in each class you can have multiple techniques. Emulsion polymerization, it may be single or double emulsion polymerization, dispersion polymerization, suspension polymerization, and sedimentation polymerization. Depending on the type of method you are using for preparing the microspheres, you will get different size of microparticles. And for getting a particular size range, you may opt a particular method. Okay. Or vice versa, you can say. Say for example, as you are seeing in this table, that for emulsion polymerization, size range is obtained is generally 0.01 to 1 micron. For dispersion polymerization, 0.5 to 1, 0.5 to 10. For suspension polymerization, it is 50 to 500 micron. Sedimentation polymerization, more than 1000. For solvent evaporation method, 1 to 100. And for hot melt microencapsulation, 1 to 1000. Solvent removal, 1 to 300. Spray drying, 1 to 10. For ionization method and size extrusion method is 1 to 300, and for phase inversion it is 0.5 to 5 micron. So please do remember, and from your exam point of view, it is utmost important to to present this table with reference to your particle size, because particle size is very important when you are designing a or developing or preparing a microparticulate drug delivery system, because it may affect your overall therapeutic effect. It may affect the targeting. So that's why the size is very important. Now, what are the techniques of microsphere preparation? Solvent evaporation, hot melt microencapsulation, solvent removal, spray drying, ionic gelation, size extrusion, phase inversion microencapsulation, Prolise microsphere technology. There are so many technologies out there. Okay, in under a one particular class, you can have multiple techniques. You can adopt any technique depending upon your drug and the polymer and what kind of release you want. Now let's discuss. Please focus on this table that factors affecting microsphere preparation. For the polymers, what are the factors which are affecting the microsphere preparation? Its concentration, composition, whether it is hydrophobic, hydrophilic, or whether it is in amorphous state or crystalline state, its molecular weight, uncapped and capped terminal and group, flexibility of chain, and so many factors there which affect actually the microsphere preparation. For drug, the nature of drug and its solubility is the prime factor. However, there are so many factors, but these are the two major factors. For the solvent, it should be natural one, or it may be that the nature of the solvent, whether it is aqueous or non-aqueous one. Okay, its safety may also be there. Its cost may also be the factor. Emulsifier, its nature and its concentration. For emulsification process, the temperature, stirring agitation speed, dispersion phase composition, continuous phase composition, and phase ratio. And drug polymer ratio is another important factor. Then the mode of solvent removal, in which way you are removing the solvent from the mixture. Either you are evaporating or by oven or natural or another means. Now let's see the emulsion polymerization. Single emulsions, water in all emulsion solvent evaporation technique it is, and double or multiple emulsion technique may also be adopted. As you can see in this flow chart, that polymer in solvents, polymer you can take PLGA, PLA in the solvent methylene chloride or chloroform. Drug in co-solvent is added and a dispersed phase is prepared, and PLGA and drug is mixed are mixed in the organic phase. Then this dispersed phase with continuous phase is added to form a O by W emulsion, oil in water emulsion. Okay, continuous phase may be aqueous one, and it may be mixed with emulsifiers like PVA, HPMC, and gelatins. So evaporation of organic solvent is needed in the next step. You can do it by atmospheric. You can do it at atmospheric pressure or applying vacuum or heating, and then the next step is collection of microsphere loaded with the active drug. You can do it by the filtration, centrifugation, or decantation, and then you will wash it and dry it, and the microsphere will be collected. Now moving to the emulsion polymerization. There are the four major techniques or four major methods, sub-methods of this method. That co-solvent method, dispersion method, multiple emulsion method, and non-aqueous method. In these methods, what you are doing, as you can see, please try to remember them, because it would be very difficult to address each and every method in sentences when from exam point of view. So it's better that you go for the flow charts for representing all the methods. As you can see here, what you are doing in all the methods, you are emulsifying the organic phase into the external aqueous phase, leading to the type of emulsion. It may be oil in water or multiple emulsion or oil in oil. Okay, then you evaporate the solvent to form the microspheres and collect the microsphere by any method, filtration, rinsing with water, or vacuum, applying the vacuum, and then you dry it and sieve it. Dispersion polymerization. Particle size we obtain with this method in the range of 0.5 to 10 micron. All of the reagents, including monomer, initiator, and stabilizer, are dissolved in an organic medium. Since the initiator is soluble inside the monomer, polymerization takes place inside the monomer droplets. The polymer beads, insoluble in the organic solvent, precipitate and the stabilizer prevents the bead flocculation. So this is the dispersion polymerization. In the suspension polymerization, uh, you adopt this method when you need a particle size unit of 50 to 500 micron. In suspension polymerization, the monomer is dispersed in a water phase with a stabilizer. The initiator is soluble in the monomer phase where polymerization occurs. The size and quantity of the particle is determined by the size and quantity of dispersed monomer droplets and by the speed of mechanical strength. The speed is very important when you are preparing this suspension polymerization. Many times when you don't apply the desired agitation, you don't get the microspheres. Okay. Sedimentation polymerization. It provides the uniform polymer beads of the millimeter scale, and it involves, as the name suggests, that the gravitational ascent of polymerizing aqueous monomer droplets in the hot paraffin oil. At the end of descent period of 7 to 9 seconds, the microspheres continue to polymerize without coalescing. You might have prepared this thing. You might have gone through that. You take the albumin microspheres are prepared by the sedimentation polymerization only. What you take, either you take the egg yolk, egg yolk, or you take the albumin powder. For the albumin powder, at least 10 to 25% weight by volume is desired. If you are having egg albumin powder, you will take the egg albumin powder of in the range of 20% weight by volume, ranging from 10 to 20% weight by volume, and then you will mix the drug in it, and at a desired concentration you will mix a little bit of water, and then you will inject through the syringe to the light liquid paraffin. Okay, and light liquid paraffin will be taken in a column, in a big uh, beaker, which is, and it is heated. Okay, this entire content is heated. When it is heated only, you will put this microsphere solution, pardon, that you will prepare that albumin from upward and then keep on dropping it. So the descent, the gravitational ascent will help in sedimentation polymerization, and at the bottom you will get the microspheres droplets, like in pearl like thing you will get, and you will dry it, decant it, dry it, you will get those microspheres. This is the wonderful and very simple example of practicing this type of microsphere. Solvent evaporation, it is most extensively used method of microencapsulation. What you do, you take the polymer, you take the drug, mix them in a common organic solvent, then add this aqueous solution containing the surfactant while stirring, and then what you will do, you will evaporate that particular solvent, so you will get the microparticulates. Okay. So for the solvent evaporation, what are the factors which affect the solvent evaporation? Polymer molecular weight and its concentration, polymer crystallization, type of drug and method of incorporation, solid, liquid or suspension, organic solvent used, types of surfactant in aqueous phase, organic solvent aqueous phase, cations, and evaporation temperature. So these are the factors which affect the solvent evaporation, and these are very important factors. You might be asked to elaborate each and every factor. Just enumerate all the methods, all the factors first of all when you are answering the question, and then go one by one depending on the score, depending on the length of answer required. Okay. Now the next technique is hot melt microencapsulation. As the name suggests, hot melt. So what we are going to do, that we are going to take the polymer in the molten temperature at Tm, and molten polymer is taken, and with the drug particles they are mixed together and they are added to the oil phase, kept at that molten temperature while stirring at the same high temperature. Then we will cool the system to get the microparticulate. We will separate and dry the microspheres. So techniques which are used for some specific polymers. Inotropic gelation technique, hydrogel microspheres they are also called. Alginate in solutions are anionic polyelectrolytes. This ionic gelation process uh, is the beauty of alginate. Alginate cross-link with calcium ion. When they come in contact with calcium ions, they are cross-linked. Okay, alginates are anionic one. Okay, and they form the cross-linking with the calcium ions. Okay, which are positive ions obviously. So this cross-linking is called ionogylation technique. This method is called ionogylation, and this is ionic gelation process. As you can see here, what you will do that you will prepare a sodium alginate solution, generally 2 to 3%, 1 to 2% solution you will prepare of sodium alginate with aqueous solution will be there. You will add the drug there, okay, and you can in the laboratory what we take a syringe of alginate microspheres and generally 18 gauze you take, uh, and then you will drop wise you will add this alginate solution with loaded with the drug dispersed with the drug. You will add onto the calcium chloride solution. Okay, calcium chloride solution will be there, and then you will add again. So the rate, the distance, these are the factors which are very crucial. The rate at which you are dropping it down, and the distance of the that syringe, or you can say whatever the mechanism you are applying for loading that alginate my solution into the liquid, and then almost spontaneously these microspheres due to ionization techniques are prepared, and again the pearl like soft pearl like rubbery, you will get some very glowing microparticle you will find that there. And then what you can do, you can decant the calcium chloride solution and then just dry these particles, and you can get it. And this is one of the very simple techniques which you apply in the your laboratory setups. So you must know the idea between the concept between the these alginate microspheres. Okay. Now moving to the characterization part. So this was all about what we have discussed so far are the various techniques we have covered. And in techniques we have discussed also in the laboratory setup, how in laboratory setup you can prepare. Okay, you can like albumin microsphere we discussed alginate microsphere. They're simple things. You do it in the lab, but the concept must be known to you. Until unless you discuss, you know the concept, you can't understand how the microsphere is going to behave, how it is going to load the drug, or how it's going to release the drug. So the evaluation part comes after the preparation. That first of all, it's surface morphology. As you can see in this slide, that's a microsphere surface morphology is seen in the, it is a SEM picture of a microsphere. You can see it also through the TEM and light microscopy. However, you need, when the particle size is very less, you need the SEM. So it's a SEM picture. By this way you can see, have an idea that what kind of surface is there, whether it is rough, whether it is smooth, whether it is having some pores there. So depending on the morphology, you can correlate that morphology with the drug release parameter, drug release data what you are going to have. Micromeretic properties, just like powder micromeretic properties, particle size uh, by any of the methods like TM, SEM, CLSM, and that sieving. Flow properties, angle of repose, Car's index, compressibility index, Horner's ratio, density in the bulk or tap or true density. These microbarometric properties help you to correlate the data again with the drug release profile. Encapsulation efficiency like drug content, percent drug loading, or this entrapment efficiency must be uh, characterized. And for this, generally we dissolve the a certain amount of a known amount of microsphere into the known amount of a solvent. Generally, a common solid. Let's say, for example, you take the methanol directly, so that each and every component is dissolved into the methanol, and then you stir it for a time being, maybe sometime for 3 to 4 hours, or maybe sometime overnight, depending upon the nature of drug and the polymer. And then you take you assess it spectrophotometrically. You come to know that how much drug is loaded into that certain amount of microsphere. By this way, you can calculate the amount of microsphere which you need for your dissolution studies or for your doses. Okay. Crystallinity is another important parameter. Like it can be done by the DSC, differential scanning calorimetry, and XRD, X-ray diffraction. You can go ahead with that, and depending on the peak, portion of peak, in the DSC temperature and the peak portion, in XRD again the peak portion and the diffusion of peaks. More the diffused are the peaks, more it is amorphous in nature. So generally we can have the, however this is an entire different science, but I'm just compiling so that you can put it in your exam, you can reply in your exam properly. Now, next set of characterization, now we are moving to the release profile. In vitro release done by the dissolution and through the dissolution apparatus using standard dissolution apparatus on the basis of percent loading. You will see with the passage of time how much amount of drug is being released and prepare the data and spectrum, all the data, the spectral data is converted into the drug release profile, and the the release models are studied, the type of release, the order of release, the mechanism of release studied by the various models, pharmacokinetic models. Mucoadhesivity, we will be discussing it in mucoadhesion also, that in vitro wash-off test for mucoadhesive microsphere you perform, how much mucoadhesive it is, how much it can retain to the mucosa. We study it and we perform it in disintegration apparatus. We will also study in mucoadhesion, that in mucoadhesion, in disintegration apparatus, you study this in vitro wash-off test. Floatability, as the name suggests, we are just seeing that how much up to which time the microsphere remain buoyant and they are keep on floating on a particular surface. Okay, that is the you can characterize with the floatability parameter. In vitro drug release study, you perform with the various things, the permissions studies you also perform. If required, permission study can also be done, provided it solves our purpose or it is desired. Then last, stability studies. Stability studies are generally done in the harmonized conditions and with the harmonized guidelines. We can go for the short range, medium or long range stability studies for the particular set of temperature and humidity or any other parameter desired, depending on the nature of drug and the polymer. Now, release pattern of microspheres, let's see that biodegradable polymers. For the biodegradable polymers, degradation of controlled monolithic system is for this kind of system, the drug is dissolved in the matrix and uniformly distributed drug release only. Drug releases only on degradation of matrix. So drug is released only when the matrix is degraded. Okay. While in case of diffusion control monolithic system, diffusion of the drug is followed by the degradation of the polymeric matrix, or it may be simultaneous. Okay. In the biodegradable polymers itself, diffusion control reservoir system, as the name suggests, there is a reservoir, drug releases through the rate controlling membrane RCM, which erodes, that rate controlling membrane erodes only after the complete release of the drug. Okay. In case of erodible polyagent system, drug is attached chemically to the matrix and rate of biodegradation of matrix is less than the rate of hydrolysis of drug polymer linkages. So by this way we can have this erodible polyagent system. Let's focus now on the non-biodegradable polymers. In the reservoir type system, penetration of water through the rate controlling membrane RCM is the first step, and then what happens that the dissolution of drug in the penetrating dissolution fluid occurs. What next? Partitioning of drug is there through rate controlling membrane and diffusion of drug across the diffusion layer occurs. But this way reservoir type system works and drug release is done. In the matrix type system, what is the release pattern? The release is governed by the state of drug in the dissolved or dispersed, whether it is dissolved or dispersed in the matrix. So this is the governing factor for the matrix size system. Now, some other types of microspheres, what kind of microsphere types may be that they may, depending on the release profile, depending on the site of action, they may be gastroretentive microsphere. They may, in the gastroretention, they may be floating, high density or mucoadhesive microspheres. We will be discussing a complete separate lecture on GRDS, that is gastroretentive drug delivery systems. Then it may be magnetic microspheres where some magnetic particles are there so that we can guide through the external magnetic field, as we have discussed in targeted drug delivery. In case of brain tumor, we target the drug with the help of these external magnetic fields, provided that microsphere is containing some magnetic particles inside them. Okay. Now in the gastroretentive microspheres, low density of the gastroretentive dosage forms creates the buoyancy above the gastric fluid. They float in the, because they are having the low density. They just like micro balloons, micro sponges. Okay, they just float. Stomach location is anatomically lower than the pyloric sphincter. So high density drug retain the dosage form in the body of the stomach. Okay. So in the high density, if you prepare the low density, it will float. In the high density, it will be clogged into the pyloric sphincter. In both the way, we can retain the drug in the gastric environment. The above purpose may be solved by both of the approaches, but it depends on the drug and the polymer what you are taking for preparation of the microparticulates. Another approach, that drug or excipient which slow down the motility of the GIT, gastrointestinal tract, may be adopted, or the bioadhesion to the gastric mucosa may also be adopted for the gastroretention. Another approach may be swelling to a larger size. Sometimes you develop a delivery system in which the polymer becomes swollen when it is getting the gastric fluid and other biological fluid. This swelling delays the emptying. So slow emptying of the dosage form or delivery system through the pyloric sphincter is there. So thereby we are increasing the mean residence time in the gastric region. So this solves our purpose of gastroretention by any of these approaches we can do. Magnetic microspheres, like microparticle system with added magnetic particles in the matrix. The system can be targeted to the desired site of action with the help of external magnetic field. The magnetic microspheres have been prepared for various anti-tumor and anti-cancer drugs like doxorubicin, methotrexate, adriamycin, interleukin-2, etc. So you will have to give some concepts, some examples whenever you are putting, when you are discussing any type of microspheres. Okay. Now, what are the applications? As far as the application is concerned, they are used in the targeting of tumor, in targeting tumor, vaccine delivery, protein peptide delivery, control drug delivery, gene delivery, diagnostic uses, antigen delivery, and brain delivery. You can have specific example of each category. Just add this depending on the length of answer required. You can pinpoint the further examples for each category of application. Okay. Now let us summarize what so far what we have learned in microparticulate system. That microparticulates are free flowing particles ranging from 50 to 300 micron, and for developing the microparticle you need two major components, drug and the polymer. Okay, the methods of polymerization, we have discussed the four major types of polymerization methods. Okay, that it may be emulsification, that gravitational and suspension polymerization. All these kind of polymerization, whatever we are using, or you can say solvent evaporation method, solvent removal method, the techniques may be, sub techniques may be there. Just remember those techniques, their basic concept, and try to put them in the flow chart or in the ray diagram, so that you need not to express the same thing in the the words or in the text. Otherwise, you will have to write quite long. So it's better to use more and more infographics, table, figure, ray diagram to answer your question, specifically when you are answering the questions of no degree systems and others which demand more and more content. As far as the characterization of microspheres are concerned, types we have discussed. Characterization, we have discussed that surface morphology is very important. We can do it by SEM, then the micrometric properties, okay, and after that the entrapment efficiency, percent loading, in vitro release. In vitro release, you know, these micrometric and the like flow properties, density, etc., and the surface morphology, they must be studied in tune with the in vitro drug release studies. Okay, you should correlate these things when you are expressing in terms of your research work. As far as the types are concerned, we have discussed the magnetic microparticulates and the gastroretentive microparticulates. The various approaches we discussed. You must learn the examples of each and every category, and specifically with the applications, several applications we discussed. We must go with the application part very technically, because sometimes only the question on the application may be asked. So the application part you have discussed it in the, like in types. So you just put the particular type, whatever the example you cite in the types, you can put it in the application part. Okay. So 2, 3, 4 examples, so that they may fit into any type. Either you can also discuss them in the type, you can also discuss them in the into the application part. Okay. You can also discuss them into the method part, like we have discussed in the albumin microparticulate or the ionization techniques. Okay, just learn the examples. More and more examples will enrich your knowledge, as well as it will help you to score good. So far it was all about the microspheres. Hope I could address your need of this particular Novatech system. We will be coming up with the new modules and new lectures on some more new Novatech systems in our next lecture. Thank you. Thanks a lot for being with us. Happy learning.